Hello everyone, I'm Ray Zhu. I'm going to present our work on single-view metrology in the wired in collaboration between UC San Diego and Adobe Research. Given the image on the left, single-view metrology can recover the scene and the camera parameters in 3D, only up to ambiguity in a global scale factor. For example, the two solutions in the middle. We present an approach to single-view metrology that can recover the absolute scale of a scene, represented by 3D heights of objects or camera height above the ground, as well as camera parameters of orientation and field of view, using just a monocular image acquired in unconstrained condition. Our method enables applications including virtual object insertion with absolute scale estimation for realistic results. Most of the previous works in structure for motion from uncalibrated cameras, monocular camera calibration in the wired, and single image depth estimation suffer from scale ambiguity, which is inherent to the projective nature of image formation, and resolving it requires additional information. One seminal work to address this problem is single-view metrology, which uses reference objects such as windows or average person height to infer the size of other objects. In this paper, our goal is to leverage modern deep neural networks to build a robust, automatic single-view metrology method that is applicable to a broad variety of images in the wired, and predicts both camera calibration parameters as well as the scale of camera and object heights. We model the scene in the wired with full perspective parameters. Given the camera and object parameters, the reprojection of the object should ideally match the detected object bounding box in the image. In our pipeline, we have two sets of modules. Given a single image, we have the camera estimation head to estimate camera parameters, and the object heads to estimate object bounding boxes, object heights, and key points per person, which helps getting pose-dependent heights. Based on these estimations, we have camera height estimation module to estimate the camera height. Because we do not have supervision on the camera height, we reproject each object onto the image plane and constrain training with a bounding box fitting loss. For the subsequent layers, we refine the object height and camera height by further minimizing the mismatch between the reprojected boxes and the detected ones. We also enforce categorical Gaussian priors on the estimated object heights. We use a subset of COCO dataset with 2D annotations for weekly supervised training of our network. We filter the COCO dataset to acquire images of objects on the ground with A model bounding boxes to arrive at our dataset, COCO scale. Our method is qualitatively compared to a classical method of probabilistic graphical model with state-of-the-art components through the application of virtual object insertion with estimated scale and camera parameters, where our method demonstrates more reasonable scale estimation results and better robustness. We also conduct A/B user study on the virtual object insertion results, where our model improves with more layers of refinement and estimating human poses to better infer human heights, as well as advantage over the baseline method. For quantitative evaluation of the object height and camera height estimation, we leverage datasets with ground truths from Kitty and IMDb 23K celebrity dataset. We report quantitative results on bounding box reprojection errors, object heights, and camera height estimation on Kitty and IMDb 23K. We demonstrate by learning to refine camera height and object height estimation from bounding box reprojection residuals in a cascade manner, we are able to significantly improve the estimation results. We also achieve state-of-the-art camera calibration performance on the camera calibration dataset. In conclusion, we propose a state-of-the-art single-view metrology method for images in the wired that performs geometric camera calibration with absolute scale, such as horizon, field of view, and 3D camera height, from a monocular image. We demonstrate its application to scale consistent object insertion in unconstrained images. We also publish datasets and benchmarks in this task for future research. Thank you.